after all of that, arrange to sort of introduce Andrej. Hopefully everyone knows you anyway, and you're going to tell us about this really, really exciting work that you've just published.
Yeah, thanks everybody for joining in. Yeah, I'm very excited about this work that I've been doing with Will and Neil well, basically since I came to Waterloo, and so I'm gonna tell you about it. And basically, it's now kind of got some nice closure in a sense that we looked at this anisotropic assembly bias in theory, like in simulations first, and then we looked at it in data, and it seems to be there. So we put this paper on arXiv last week, and so I'm excited to tell you about this. As I said, like really, I'm gonna, since we know each other, like I really don't mind being interrupted, ask questions if I'm going too fast or something, or if I'm not explaining something well, or like it's better to interrupt me, maybe, especially the students, if then let me go and ramble on. So, okay, so just a brief outline of what I'm going to talk about. I'm going to basically start with why do we do and what do we want to achieve with basically large-scale structure galaxy surveys. And so I'm going to go through power spectrum, versus space distortion and bias. Then I'm going to define what do we mean by this anisotropic assembly bias that we call, it's showing up with AB. So AB doesn't stand for assembly bias, it stands for anisotropic assembly bias. Then I'm going to show you some results from simulations where we looked at this for dark matter halos in numerical simulations. Then we went out and looked at this for Bose galaxies. And at the end, I'm going to just wrap up and summarize. So, right. So to start off, we have this very successful CDM model that is describing a lot of the phenomena in the universe, and it has a lot of also problems. So it's highly successful in predicting and describing the universe. It's not very successful in understanding. So our goal is really to basically, and our hope is to learn more about the universe by basically probing larger data sets. We found this cosmological information to be contained in many different observables, but one of them that kind of stands out, we've learned over the past several decades, is that actually inhomogeneities are the dominant source, and mainly we get this information through the two-point statistics of fluctuations. So cosmic microwave background has been a prime example of this, and most of the constraints of cosmological parameters we have really come from the fluctuations in the temperature that we see in the CMB from WMAP and Planck. However, since CMB is just a shell, let's say, plus some intervening matter, large-scale structure is fully, basically probing the galaxy field, is fully 3D, so it's expected to do even better, right? And galaxy redshift surveys are a way to do it. It's been established. They've been proven to work, and it's a promising way for future galaxy surveys to how to constrain cosmology. So this is what we're doing, and so what do we actually measure with large-scale structure surveys? So we have this from SDSS, like how galaxies look on large scales. Of course, here this is not matter; these are really galaxies. But we usually work at the level of the matter field, where we define basically this overdensity field, has some fluctuations around the mean matter field, and then we can measure these two-point statistics. For example, either the power spectrum or the correlation function, which tells us basically the variance of this overdensity field on different scales. And this in principle depends on the full direction, the vector, but because of the cosmological principle, since the universe is homogeneous and isotropic, these only depend on one variable, that's power spectrum, that's the scale, or correlation function is the distance. And so that's very nice, because then we can compress basically all this information into basically just this one line, roughly. And this plot from Planck paper really shows the agreement between different observables and the matter power spectrum on top of these. These are all normalized to show the same matter power spectrum. So this is really nice. It shows that all these over a wide range of scales, these all agree very well. However, this, of course, is not, we don't, first of all, observe the real space positions of matter. and we don't observe matter at all. So, so what do we really observe? We observe objects in redshift space, so we don't observe them as they appear in the, as they are moving because of their Hubble flow. There is also peculiar velocity contribution. So in principle, we don't even measure positions, we measure redshifts. These peculiar velocities will shift galaxies and distort them in the radial direction. So we will not really know what's the real position of objects in redshift space, the one that we observe in. But it's important to know that on large scales, these velocities are kind of driven by the matter field itself, and they are scaled with this growth rate that I'm going to tell you more about a bit later. What actually happens is that in these linear regimes, so where the overdensity is on very large scales, you get an amplified clustering in the radial direction. So this is this famous Kaiser formula, which tells you that in the radial direction, you have this F mu squared. So now this mu is just the angle between the line of sight and from the line of sight, roughly. So here I'm plotting basically how the isotropic power spectrum looks like. This is just a mock-up plot. This is not a real power spectrum, but it just shows that if you look at the radial direction or the transverse direction, it's the same in real space, while the bottom figure shows that in redshift space, you get more clustering is amplified in the radial direction. And so the redshift space distortions are one cause of this anisotropy, and the level of this anisotropy is sensitive to this growth factor. So if this F is 0, if there are no redshift space distortions, we would expect completely isotropic power spectrum. Another complication is, of course, as we said, we don't observe the matter, we observe tracers of the matter field. So everything that we use for clustering analysis is really just a bias tracer. So for example, galaxies, halos, voids, 21 centimeter, or any other tracer that we looked at are all bias tracers, meaning that their overdensity field is related in some way to the matter overdensity field. And the simplest thing that you can write that really works well on largest scales is this relation between the overdensity field and the matter field, which is just linearly biased. So there is this B, for example, for galaxies here, there's this bias called linear bias BG, which just tells you that when you compute a power spectrum, that your observed power spectrum will be scaled version of the linear matter power spectrum with this bias term. And so, so this is usually what works on large scales. And so I try to make this, so you can also visually see how different tracers can be differently biased. So in this figure on the right, these are like two, so you see underlying matter field with this web. So that's really not what you don't see in observations, but you see these points. And so, for example, you can roughly maybe see that on the top panel, the green points are less clustered than the red points on the bottom. The red points appear more close together and more kind of non-random. So that's what we mean by when we say that a tracer is more biased compared to the matter. So the red one will have a bigger bias than the green one. So this linear bias actually depends, since it's a scalar, it depends on basically two quantities, the halo mass. So more massive objects are more biased. So when you observe bigger things, the power spectrum will be more amplified. And also there is a temporal evolution. So things earlier on are more biased than later on. So that's important to know. But in redshift space, if you want to now incorporate this all into one picture, the bias tracers on large scales do not have a velocity bias, meaning that when you write now the redshift space power over density field, for bias tracers, the bias will appear only here and not for the redshift space distortion. That's just because the matter and galaxies flow with the same velocities on large scales. Okay. So now, how does this all look like when we combine, for example, for the galaxy power spectrum in redshift space? So in this linear theory, we have just some non-mu dependence term, and then we have this mu dependent term, which is the RSD. And so now your power spectrum became 2D suddenly. So people usually work in either the full 2D, or you can expand it in multiples using Legendre polynomials. And I will be talking a lot about multiples and quadruples. So we usually work at the level of, for example, the monopole is just like when you average out over all the mu's. So, so the monopole depends mostly on the bias, right? But also on the level of the amplitude of the anisotropy F. However, the quadrupole is directly proportional to the growth rate. So if you don't have any anisotropy, the quadrupole is 0, right? So in real space, for example, the quadrupole is 0. So this is, I was showing you these plots, these are like mocks, but this is really what the BOSS survey is measuring for the 2D power spectrum. So these are the real observations coming from galaxies. So you see that the power spectrum is not circular, it's more extended along the radial direction. And now this growth rate that I was talking about is very important parameter. So this is like this is actually defined as the logarithmic growth rate, where this dA is the growth factor. This is how fast structures grow. And in GR, there is a prediction for this parameter, is this amount of matter at a given redshift to this power. And this is, hence this parameter, measuring it from the redshift space distortions, is very important, since you can test gravity, you can constrain neutrino masses. It depends also on neutrino masses, dark energy models that change the redshift evolution and so on. So currently, these are some constraints that I picked up from the Planck paper, and you see that they are a bit all over the place, but most of the best ones are roughly 5 to 10%, depending on which binning you take, while future surveys are expected to do much better, of course. So we need to be very careful with how well can we, what is the theoretical error and the systematic errors on this parameter. So we need to know this F parameter very well. And I'm going to talk about an effect that basically kind of is degenerate with this F. So, okay. So on top of all of this standard picture, this linear bias is not really just dependent only on halo mass and redshift. It also depends on other properties. So when you fix halo mass and redshift, there are other dependencies that show up. So for example, this plot I was showing you before, the difference between the green and the red are actually not in the mass, but they are in concentration. So you see that the red ones here are more concentrated halos. They are more clustered than the less concentrated halos, while on the rightmost right plot, you see various other dependencies of this bias at different halo mass. So you fix halo mass, for example, and you can see that, for example, this red line is always on top of the blue line, meaning that old halos are more clustered than young halos for a given redshift and mass. So this effect has been shown in simulations and detected in simulations, but it has not been yet found in real data. And the main problem is, of course, this thing, that how are you sure that you're measuring the clustering of objects for a fixed halo mass? Because halo masses are a bit difficult to determine. So all of the trials to detect this in real observations have usually failed because there was some bias in their measurements for the halo mass. Okay. So now I want to move on to this effect that we are looking at. So we didn't consider any like non-linear elements of the overdensity field. So this is where we stopped. Basically, we had this bias term, we had the redshift space distortions, but there is another term that is directly proportional to the overdensity field at the linear level, which is this traceless part of the tidal field. So the tidal field, the traceless part of the tidal field is defined like this in Fourier space. So it's this Sij is directly proportional to the overdensity matter. And so if you're, this Bij can only be things that correlate with the tidal field, and only non-scalar properties can correlate with the tidal field. So before for the assembly bias, we were only considering scalar properties like formation history, age, spin, concentration. These are all scalars. So now what about non-scalars, right? So we do know that non-scalar halo properties are correlated with the tidal field. For example, this cartoon I made basically showing that if you have a halo in an isotropic field, it should be spherical, right? But then if you add if you have an anisotropic field, the halo will orient towards will orient accordingly. And so if you have an overdensity here and here compared to other parts, you will have halo oriented like that. And if you have vice versa, you will see halo oriented. So we do know that these non-scalar halo properties, for example, the shapes, but also the velocities will be correlated with the tidal field in this way. So actually we went out and measured these across many scales. So here I'm just showing basically how correlated are halos and tidal field. And for reference, I'm just showing the matter power spectrum here. So if you correlate the tidal field and the full shape of the halo, you get these blue lines. So you see that they are correlated on all scales, basically on the largest possible scale. So halo shapes are kind of correlated with the large scale tidal field on all scales. This is also true for velocity dispersion and also for angular momentum. So great. So now we know that these things are correlated, and we can now also simplify this a bit. Since you assume that things on the plane of the sky are the same, however you rotate it, the only term that survives is this BZZ, so the ZZ component. This is what we will call BQ, and we call it BQ because it basically has a quadruple shape in the mu variable. So let me just summarize here. So basically, we went from this galaxy overdensity field in redshift space, which was this simple one here. This is the Kaiser term. We went now to something that has this BQ here, which is kind of modifying the bias. And there is another term that is completely degenerate with the growth factor. So this just adds. And this BQ is what we call the anisotropic assembly bias. Okay. So it can cause anisotropy even in the real space. So for example, if you put F to 0, your power spectrum will still be anisotropic. And it's an additional source of anisotropy in the redshift space. So, and completely degenerate with F. So this is a problem, right? So if you want to measure this F, you usually measure the monopole and the quadrupole, and you get the F. But if you have something that is very degenerate with it, then you don't know if you have a big BQ and small f, or big F and small BQ. So why people usually assume that this is 0 is it's only 0 if your selection is independent of halo orientation. So for example, if you're making your selection on scalars, then this should be 0. And also, so we said that halos are correlated with the tidal field, but tracers living inside those halos could be completely randomly misaligned. So that is another part. So you basically need two effects to show up in order for this to be non-zero, right? So you need to be orientation dependent, and you need to have your tracer being aligned with the halo orientation. Okay, and so one way to check this in simulation is basically, we know for halos how oriented they are, and we can go back to real space, not like in real observations. So in the simulations, we know the real space positions of halos. So let's remove the redshift space distortions for now. Let's just take halos that are aligned either like this, like the dashed line over here, or let's take halos that are aligned perpendicular to the line of sight. So the ones aligned along the line of sight will have higher velocity dispersion across the line of sight, and will have bigger extent along the line of sight. They will also have the tidal field component negative, right? So this will be important. And vice versa for these other halos. So since we are in a real space, we expect that there is no anisotropy in the power spectrum, meaning that the quadruples, it is proportional to F is 0 in this case. We expect that the quadruple is 0. And if the quadruple is not 0, that means that the only source of quadruple that can show up is this anisotropic assembly bias. So then we went out and measured these things. So we measured the quadruple of the halo matter field. So let's just focus on, so going from top to bottom, these solid lines are really these halos with solid lines. So, and the difference between the orange and the blue is just whether we're considering low values of extent or low values of velocity dispersion. So in this case, you see that the quadrupole is very non-zero, right? So, and in the opposite case, where you look at the dashed halos, these are the dashed lines on the bottom. They're kind of symmetrically different from zero, one against each other. Okay, so to kind of estimate this, what is the size of this effect is really, so in Redshift space, this growth factor is roughly 0.7 or something like that. When you look at these extreme halos, the difference between these BQs can be of the order of 1 and 2. So you see that this is a huge difference compared to what you're really trying to measure. Okay. So, right, I'm just going to take a little break here and see if there are any questions, because now, so that was for halos in simulations. And now I'm going to move to galaxies, so completely different part. So are there any questions so far?
Mike's been quite active on the chat. Do you have anything you want to ask Mike directly?
Sorry, I was not looking at the chat.
It just went by very fast, so I lost what the definition of BQ was. And
oh, okay.
why it depends on the density and not on the tidal field, which is what you started with.
Right. So, okay, I started from so here. This was the BIJ, the full thing.
Okay.
And then I said that basically I moved here. Sorry, and I said that since it doesn't matter how things are oriented on the plane of the sky, the only one that survives is the ZZ component.
What happened to the SIJ? It's gone between the top and the bottom.
So SIJ is related to the density field, right?
Yeah, it's related, but I don't see the leap from the top to the bottom. I mean, it's a tidal field.
Go back to your previous slide, Andre.
Yeah. So here it is. Here is the SIJ.
Whoa, slow down. I got to think about that for a second.
Okay, sorry.
Okay, so you're substituting that in, and then you're doing something else.
Right. Okay. Right. So if you consider, for example, say, so like the parallel component, line of sight component, right? Right. They'll give you this mu squared minus 1/3 that appears in the quadrupole.
Yeah, that appears over here, right? So this is the parallel component, only has the mu squared minus 1/3.
I can't do that in my head. What happened to all the K's and everything else? Are they gone too?
Okay, so, no, yeah. So if you only consider the radial one, that's like kz over k squared. That's mu squared.
I guess so. Yeah. Again. Okay. Now I agree. But yeah, that went totally past me very quickly. If
sorry.
you don't do this every day, then you're not going to follow the chain, right?
Sorry about that. Yeah. So so this has all the components. If we only consider the radial, here will be like k parallel over k squared. K parallel over k is mu, so this will be like a mu squared here. And ZZ is just 1 here, so it will be 1/3. So that's what happens here.
Okay, that makes more sense. Thank you.
No problem. So sorry if I went too fast over that. So, but the end result is that there is a term that appears here with the mu square dependence, which cannot happen if you're looking at scalars, right? So then if you split then what we did here is that if we split on these tensor properties, then this kind of shows up and can change your quadrupole even in real space. Okay, are there any other questions? Okay, if not, So this was kind of encouraging that we saw this effect in simulations, and for halos, they seem to be rather significant and important. And so we were wondering, what about galaxies? And now there is a big leap, right, from galaxies to from halos to galaxies, since galaxies are not necessarily have to be aligned with halo shape, sorry. But one sample that we do know that is kind of correlated with aligned with the halo shapes are the LRGs. So the LRGs are most of the galaxies that are in this BOSS sample. So the BOSS sample is the Baryon Acoustic Spectroscopic Survey that's part of SDSS that has roughly measured more than 1 million galaxy redshifts in this redshift range from 0.15 to 0.7 is the main redshift range where most of the objects are. It uses this 2.5 meter telescope, and this is roughly all the plates where for the North Galactic part where these spectra have been measured. And most of the targets were these luminous red galaxies, also known as LRGs in the community. And these are these elliptical galaxies that have roughly halo masses of 10 to 13. And their bias, their linear bias, is roughly of the order of 2. And there are two samples. I'm showing here the redshift distribution of these samples. So the low Z is this at lower redshift. So this is this green curve over here. And then there is the CMAS sample, which is the blue one over here. So usually you split them into these two redshift bins, and they are completely independent in redshift. So BOSS measured also part of the South Galactic cap, which actually we don't use it in the further analysis, but just because it doesn't add to, it's a smaller area on the sky, so it doesn't add too much. And, okay, so now this is, so we saw that in simulations, if we only took like split halos based on their orientation, we found different quadruples. Let's try to do the same thing here with the galaxies as well. So the main idea is let's find some non-scalar property of the galaxy, split on orientation basically, or split on that quantity. In this case, we will use the velocity dispersion, and then look for differences in anisotropy. So since in galaxy surveys we are already suffering from the redshift space distortions, this will only add to the anisotropy. So you need to look at differential anisotropies between the two subsamples. And that's basically our idea in this. So, however, we also try to be a bit more careful about all of these things. So for example, we need to be careful, we need to be sure that our subsamples have matching redshift distributions. Since the growth factor changes with redshifts, you want to be completely consistent with what part of the subsample you're taking. So again, these subsamples can have different biases and these anisotropic assembly biases. So what we actually try to do is let's just be completely agnostic and say, let's find subsamples that have matching monopoles and matching redshift distribution. So if they have matching monopoles and matching redshift distribution, that means that actually matching redshift distribution just tells you that the window function is completely the same. So if you have matching monopoles, you have to match quadruples as well. Since there is no reason why the quadruples should be the same if the F is the same. So this is a crucial point that we're trying to basically, this is the test that we're doing. We're trying to build, we don't really care about a particular model of the redshift space distortions power spectrum. We just say, if the monopoles match and the redshift distributions match and the growth factor is the same for all the samples, then the quadruples must match. And any evidence of the contrary is then evidence for existence of this anisotropic assembly bias. So how do we do this? So we need an orientation dependent galaxy property, right? So some non-scalar thing. What people have measured is a lot of these galaxy properties from the spectra of each of these BOSS galaxies. And we do have 1D velocity dispersion for each of these galaxies. And we do have stellar masses. So these stellar masses are some scalars. Velocity dispersions are not scalars because they're just like 1D projection of the velocity tensor. So how do these look like? So this is like a big blob of data points. So you see basically the stellar masses are in this range from 11 to 12 roughly solar masses, 10 to 12 solar masses, and the velocity dispersions are roughly 200 to 400 kilometers per second. So this for one of the samples. You can also see one thing that will be a bit important for later is that while the velocity dispersion don't really change with redshift, so all of these histograms are kind of very similar, the stellar masses do have redshift evolution, right? So moving to a higher redshift, so for example, this dotted line shows a bit of different distribution of stellar masses. So when we make like a naive split on sigma star, so saying like, oh, we want high velocity, big velocity dispersions, meaning that these will maybe be aligned along the line of sight, or like low velocity dispersions across the line of sight, we're not really splitting only on orientation. So we're splitting on orientation plus the galaxy mass, since the velocity dispersion depends on galaxy mass, right? So effectively, that means that we're actually splitting on different mass, actually means splitting on different bias, and that will give us different monopoles and quadrupoles. So our goal is actually to match monopoles. So we use this additional scalar, the stellar mass, to remove this dependence on the bias on the mass. So our actual goal is basically to then make subsamples that either have high stellar mass and low velocity dispersion, or low stellar mass and high velocity dispersion. So this will be kind of orientation driven, and not just a relation between the stellar masses and velocity dispersion. So let me just show you really quickly how these subsamples look like. They're shown now here. So the blue ones are these high velocity dispersion, low stellar masses, and the red and the pinkish ones are the other ones. Note that they overlap here, but that's just because of the redshift evolution. So they don't overlap in each of the redshift bits. Fine. So as we said, we need to also match the N of Z. And if there was no redshift evolution, this would be really easy. But since there is this redshift evolution, we try to account for all of these. So basically, we split in many different redshift bins. We compute percentiles in each, and then we split based on percentiles in each redshift bin. And this, by definition, gives you then matching redshift distributions of the two subsamples, the blue and the pink. So now, again, we're kind of matching the N of Z's. We want to match the monopoles also. So how do we do that? So we start looking at these like a bit of a complicated plot, but I try to make it step by step here. So first thing, in each of the redshift bins, we split our sample into these 25 grids. So in each of them, there's like 5 times 5 samples. So here will be like low values of stellar mass and low values of velocity dispersion. And here will be very high values of both, right? And all the other ones. So for each of these pixels, we compute the monopole and take the ratio with respect to the full sample. And what you get, okay, so what you get is basically this plot here that shows you basically some amplitude of the monopole when you make these little splits, and you can basically really see now the dependence of the monopole with respect to these values of velocity dispersion stellar mass. So what is really nice is that when you overplot just these contours just to see things clearer, everything makes sense. So low values of stellar mass have smaller bias, so you expect things here to be more smaller amplitude, while samples with high velocity dispersion, high stellar mass are more biased, right? Okay, so we said that we want to match the amplitude. So we basically take these two lines like that, and we select these corners, right? So these samples will have since they're following this trend of monopoles, they will have matching monopoles and they will have matching N of Z, right? So, and this is the same sample that now, how it looks like in data space, not in percentiles. So what about the quadruples? So again, I'm showing here the monopoles, but let's look at what the quadruples, how they, are they also matching, right? And so this is the quadruple. So you see that if I go back and forward here, so these are monopoles and these are the quadruples. You see that the quadruples are completely perpendicular to the monopole contours. And this is already showing us that we are matching monopoles, but we are not, we're having very different quadruples since the contours in the quadruple plane are completely perpendicular to the monopole plane. So, and yeah, so just to summarize this, we try to match the monopoles and N of Z and to see if we match the quadruples, and we don't, and I will show you now how much we don't match the quadruples. So these are the results, right? So if you take these two subsamples I was talking about, so if you look at their redshift distribution, so there are two dashed and dotted curves here compared to the scaled full sample redshift distribution. So you see that they match rather well. If you look at the right plot, on the top you see matching monopoles, so they all match within the error bars between the two subsamples, but while their quadruples are kind of different on all scales. So of course some are overlapping because the error bars are too big, but you can see really by eye also that on all scales there is some difference in the quadruples. And this is not only for the CMAS, we looked at the low Z as well. So in the low Z, we also have matching a number redshift distribution and matching monopoles on the top here in the right panel, and very different, significantly different quadruples in the bottom part. So yeah, so now, of course, we want to quantify the significance of this. And in order to do that, we use mock galaxy catalogs. So there are like thousands of mock catalogs which kind of have the similar clustering and redshift distribution of mock galaxies. So whatever you do to your data, you can also do in mock catalogs. However, these mock catalogs have not been created with all these tidal effects, right? So we don't, for example, know the velocity dispersion of halos of galaxies in the mock catalogs. Otherwise, we would have performed the same exact split on each of the mocks to get the error bars, but we don't. But luckily, since we're matching monopoles, we can just randomly subsample mocks. And we will also match the monopoles by just the fraction of whatever our subsamples are, and they are like 1/4 of the full sample. Then we do the same thing, we cross-correlate each of these subsamples with the full mock, and then we have like thousands of mock measurements of the multiples, and then we try to basically estimate how multiples between two subsamples differ from each other. And so let me just show you quickly here the results of this. So for CMAS, as we've seen before, the monopoles agree very well, basically independent on which scale you go to. So this is so the shaded area are the mock contours. So this is roughly what mocks, how much mocks vary for these A0 things. So it should be 1 if you have matching monopoles. And this line is basically the measurement we get from CMAS. However, this is for the monopole, but for the quadrupole, you see that even at very almost linear scales, you go out from the 3 sigma region very quickly as further away in Kmax you go. So the more scales you're fitting to. So you do see very different quadruples, which are many sigmas away. And so this was for CMAS. Let me also show you for low Z. So for low Z, we see the same trend. So monopoles match within the error bars, while quadruples go out from the 3 sigma plot very quickly. So this really shows us that since we're matching monopoles, we have the same growth F. The only difference could be this delta BQ. So the different anisotropic assembly bias between the two subsamples. And since these low Z and C mass are independent, we can just combine them. And when you combine them, you get a plot like this. So this just shows you basically what is the significance to get such extreme values of this difference between the quadruples as you go, as a function of to which scale you're fitting to. So you see that if you fit to very large scales, you don't have enough statistical power, but as soon as you gain, you see that this kind of grows with statistical power, so you very quickly cross the 5 sigma. So we combined signal crosses 5 sigma at 0.14, 0.15 K max. Yeah, so this is, we would say that this is the first strong evidence for the anisotropic assembly bias. And it's more at 5 sigma confidence level. So for this difference to be different from 0. So if you try to translate this, the real value of this, you get basically this delta BQ is of the order of 0.1, 0.2. While for halos in simulations, we found much bigger effect. And this could be easily explained by just galaxies being not perfectly aligned with halos, right? So that's not such a big step to take. And also note that we can only measure the delta, the difference between between the two subsamples. So note that even though this doesn't mean that the parent sample is suffering from this systematic, this still is a big systematic compared to the value we're after, right? Since we're after the F, which is roughly of 0.7, and these differences can be 0.1, 0.2, this is a big effect. And especially for future surveys, we're hoping to measure this F with 1% or 5% precision. Okay, so are there any questions now? So before I move on.
So are we allowed to ask questions?
Yeah, of course.
Okay, so Andrej, this K dependence of delta B, did you see that in simulations as well? But this is the significance, but I guess you had the K dependence in the previous, here. Yeah. So here you see it increases with K max. Although I don't know, this is a cumulative.
Sorry, this is not the K dependence, this is the significance again. So if you go back to the plots of the quadrupole, Andrej. Yeah, so this is showing the K dependence of these monopoles and quadrupoles.
Right, okay, so I mean, does the simulation look the same? Or, yeah, I guess that's, you had it, yeah.
Yeah, for halos, for example, we saw that these quadruple, so we didn't really check this for redshift space in simulations for halos, but we did in real space where there is no redshift space. We saw that like quadruples are like just a scaled version of the matter power spectrum, and they can be very different, right? Much more different than galaxies, right?
Right, now I guess the one is the question is the amplitude and the other is the K dependence. So that's what I'm trying to figure out. So you're saying that simulations, the amplitude is much bigger, but then is the K dependence similar?
Yeah, so here we're trying to focus on these linear scales where all these biases are basically scale independent. So in the simulations, for example, right? So Andrej was showing these previous plots, right? And so there, as he mentioned, right? So these cross spectra just look like scaled versions of the matter power spectrum.
I don't want to go there. It's too far. Yeah.
So it just means that therefore on those linear scales, these biases were all just constants independent of scale.
Right, but that's where you don't have the significance, right, and the linear scales. Am I correct? And where this is constant, I'm not sure which plot I should be looking at. That, and the question is, do you get a significant effect if you just focus on the linear scales?
It depends on what you call linear scales, right?
That's what I'm trying to figure out. Yeah.
Yeah. So that's why here, like, we don't go like to 0.4, whatever. Like the maximum you go is 0.2. I don't know, like what's the definition of a linear scale, but I would say like 0.1, something, one something is linear in some way, right?
This is a scale over which bias is constant. Basically, I guess what I'm saying is that if you go up to, I mean, K of 0.15 and a smaller, do you see the bias changing a lot? I don't know off the top of my head.
At these redshifts, no. Right. So, you know, so CMAS was what, like 0.4 or something?
0.57.
Yeah, 0.5 or something. Yeah, yeah. There's a K of like 0.1, 0.15. No, like, you know, the bias is fairly scale independent.
Okay.
But also you would need like basically to have different scale dependent biases between the two samples, right? In order to match the monopoles on all scales. I mean, I mean, I guess you can cook up a plan how this could happen with like varying like biases completely such that this kind of cancels out. But that happens on smaller scales. But on large scales, I don't see how you can do that.
That's fine. Okay, thank you.
Okay, welcome. Right. So we also tried some other things as well. So here we're focused on just velocity dispersion and stellar mass. We also so there is another thing that tells you about the orientation is the projected physical size, right? So galaxy on the sky can look smaller or larger, just depending on orientation, not the real size of the galaxy. So as a matter of fact, we don't find any signal when we do that. And one way to explain is that maybe this signal is washed out because the fractional scatter of the sizes is bigger than the fractional scatter in the velocity dispersion. So it may be that this signal has been kind of smeared out in the sizes. So previous work, I actually tried to see the same effect that we're after here using the fundamental plane. So the fundamental plane is this empirical relation that's kind of stems its origins from the virial relation that basically you should have the surface brightness, the velocity dispersion, and the size should be all kind of related in some way. So if you then look at, for example, deviations from the fundamental plane, this was the hope that this will tell you something about the orientation. And so, for example, there was this paper by Martins et al. That found marginal signal, basically 2-point-something sigma, when they made the split on surface brightness and sizes. Recently, like a couple of months ago, there was this paper by Sukhdeep Singh and others that used basically the same methodology using the fundamental plane, but the full fundamental plane. So now incorporating also the velocity dispersion, and they find no signal whatsoever. So this is also what kept us a bit. Since we saw this, we were like, what are we seeing and what are they not seeing? So this was kind of interesting to, so unfortunately we couldn't get which values of A and B that they used, but so we tried to like do a big grid of all the A, B values to see what happens. So let me see, let me just say something. So here we cannot anymore match monopoles as we did before. So now, when we make the split based on the fundamental plane, we really need to model the monopole and the quadrupole to get, and we do this basically using a Kaiser model. So this simple model, assuming that there is not this effect. And then we look for differences in the growth. So for each of the subsamples, we can measure the growth and then look at for the other subsample and see the difference. So that's what I'm showing here, this delta F. And you see that this value can go all over the place basically, and it's very sensitive to which A, B values you use. So these are these fundamental plane parameters. So basically this is what you get from data. So if you can like now pick your favorite, or I mean, it's really small differences in these A, B can give you big differences in this delta F. So yeah, so we kind of figure out, okay, this is very sensitive to which A-B values you use. So it may be that the difference between these two analyses has been that they've been just using different A-B values. Right, so I just want to comment on some other places where this can show up. So one interesting place where this can show up is, for example, the intensity mapping. So H1 is emitting these 21 centimeter photons, which are usually expected to be optically thin. So the medium should be optically thin to them. And so with this, you can hope to go like measure the structure to very large redshifts. However, due to H1 can self-absorb, so you may be preferentially seeing the face-on galaxies more likely than the edge-on galaxies. So if H1 distribution, so if this H1 distribution is aligned with halos, this will show up also there. So another thing that actually got us started into all of this business is that when you find groups or clusters in redshift space, this could be an effect as well. So actually we do find in simulations that if you find objects in redshift space, they do exhibit strong anisotropic assembly bias in their clustering. And also like future surveys like DESI will observe most of the targets will be these emission line galaxies that contain dust. So you can already see that, that the orientation will make a big difference. So you may be missing galaxies that are oriented edge on. So then the natural questions are, is the target selection sensitive to orientation? And also the very important thing is that the faint galaxies are the one, and actually the one near the threshold. The detection threshold could be impacted by this orientation selection the most, which is a problem since the faint galaxies are also the most numerous ones. So this is like the only way out from this is if these ELGs are completely uncorrelated with the orientation of their halo. If that is the case, amazing. So, and other places you can think of any other orientation selection effect that can show up. Yeah, so let me just summarize here. So we find this kind of new effect in clustering of halos, both in simulations and in data. It's caused by basically correlation between the large-scale tidal fields and the non-scalar halo properties. Of those, most important are the shapes, but also velocity dispersion tensor and the angular momentum as well. So the contrary to the isotropic bias, this cannot be mimicked by varying halo mass. So this is, since it's completely anisotropic, it changes the quadruple, it changes the anisotropy of your power spectrum. It's not changing just the amplitude. And these orientation-dependent selection effects of halos do produce an isotropic power spectrum even in real space, as we saw in simulations. And the problem, of course, for future surveys, that in redshift space, these are completely degenerate with the growth rate. And so just a word of caution is that care needs to be taken when interpreting these future tightly constraining RSD measurements. And yeah, and hopefully also with future surveys, we will be able to measure this bias much better. That's it, I'm done. Thank you very much for listening.
Thanks, Andrej. Right, raise a hand if you have a question.
Thank you.
Okay, I can't ask a question because I know all about it. So I can't even do the chair thing of asking a question. Ah, Nayesh, go for it.
Hi, can you hear me now?
Yep.
Yeah, so it's just apologies, my video for some reason is not working. So this is very interesting. One question is, so is this possible to break the degeneracy? So I guess I didn't quite, maybe you kind of went over it too fast. So there is a degeneracy between your F measurement and your B measurement, or your this BQ measurement. So how is it broken?
How is it, oh, okay. So, sorry, I'm not able to go fast with this, so I'll just stop somewhere. Yeah, so at this level, right, these are completely, F and BQ are completely degenerate, right?
Yeah.
So, I mean, there is, if you are using only the power spectrum, there is no way out, right? In the sense of if you're losing these large scales, you don't know, right? Because they're completely entering in the same way. So one way that actually Hirata pointed that it could be broken is by using the bispectrum.
Okay.
So the bispectrum could give you different dependencies, and so you can hopefully break these degeneracies using.
Then you get new coefficients if you look at the biospectrum.
Yeah, I'm not sure how the coefficients look like there, and hopefully they have different dependencies that when you combine, you can.
At the linear level, biospectrum is 0, so you do generate it through a nonlinear effect, but then you imagine there would be higher order biases that would come in.
I'm not sure that the bispectrum, when you account for this effect, I'm not sure if that still holds. But I'm not sure what to say. I just know that there is hope that you can break these degeneracies with the bispectrum, and there is a paper for that.
Mm-hmm. Yeah, so I guess that my worry with that would be that if you look at biospectrum, you have to introduce new coefficients. And then this scale dependence also becomes an issue, which in the linear.
Yeah, there are other approaches. For example, recently Fabian Schmidt and his group, they did a full to second order perturbation theory, like how to account for all these selection effects, basically to higher orders, and so. But then you end up with like 10 other parameters that you need to fit to your multiples, and I'm just not sure how that would work. So that's why we were kind of trying to be most agnostic here, without using any power spectrum, bias expansion models, and so on. So we were just saying like monopoles match, quadrupoles should match.
Okay, Mike.
Yep.
Mike, you have a question? You raised your hand. You're muted.
Okay. So you went by a little bit quickly. So are you saying that there's actually potentially two effects, a physical effect and a selection effect?
I would say that's the same thing. So if there was no physical effect, meaning if halos were not aligned with correlated with the tidal fields, then you can take whatever subsample you want. You're not sensitive to this term, right? But however, since they are correlated, we know that, then you need to be careful that your selection function is not orientation dependent. If you know that you're complete in your sample, so for example, if you choose things by scalars, and you know that those scalars are not affected by anything orientation dependent, then you're fine, right? So this has to be really some thing that depends on the orientation. The problem is you cannot never understand these things because we cannot run perfect simulations to take into account all of these things. Does that answer your question?
Sort of. I'm just trying to visualize it, but yeah, okay, I'll have to think about it.
Okay, any other questions? No? Oh, all right, well, thank you very much, Andrej.
Thank you.